Okay, chapter 7, 7.1, we're going to be talking about graphing exponential functions. So what exactly is an exponential function? Well, it's a function that's in this form, y equals a times b to the x power. And notice that the variable x is up there in the exponential position. Now the a, this coefficient in front of the b here, this is the y-intercept. It's where the graph is going to cross the y-axis. And then this b here, this is called the base. It's either going to be the growth or the decay factor. Now, how do we know if it's growth or decay? Well, if the base is greater than 1, it's going to be a growth function, meaning that this graph is going to grow or go up to the right. And then if the base, the b, is in between 0 and 1, like a half or a third like that, then it's going to be a decay function, and it's going to be going down or decreasing to the right. Now, notice in both of these graphs, the graph actually gets closer and closer to the x-axis. This line right here is called an asymptote, A-S-Y-M-P-T-O-T-E, and it's just getting closer and closer. It doesn't touch and it doesn't cross that imaginary line. So that's the idea. So let's look at a simple example to get you started. So letter A here, it says y equals 2 times 3 to the x power. Well, what I like to do is make a table, pick some easy values, usually like a couple negative, 0, a couple positive, like that. You don't want to pick too large of numbers because, if it's a growth function, it's going to go, right off the graph. So you just want to pick some small numbers. If we put -1 in, 3 to the -1 is 1/3. Because remember, that negative exponent tells you to take the reciprocal. Then times 2 gives us 2/3. If we put 0 in, we get 3 to the 0 is 1. Times 2 is 2. If we put 1 in, 3 to the first is 3, times 2 is 6. If we put 2 in, 3 squared is 9, times 2 is 18. Now, sometimes students make a mistake. They'll multiply these together and say, like, this is 6 to whatever power. You don't want to do that. You want to make sure you follow your order of operations, your PEMDAS. You do the parentheses first, then the exponents, and then you multiply. So that PEMDAS, parentheses, exponents, multiplication. So let's go ahead and plot these points. So we have -1, 2/3, which is right about there. 0, 2, 1, 6, 2, 3, 4, 5, 6, and then 2, 18 way up here. So you can see the graph is going to look something like this. But notice that it's growing, it's going up to the right, and that's because the base 3, see, is greater than 1, so that's an exponential growth. The 2, notice that was our y-intercept where it crossed the y-axis. And again, that's because whenever you put 0 in for x, you're solving for the y-intercept. So that's your basic graph, your parent function. Now, as far as domain and range go, you can see that this graph is going to the left forever and ever, and it's gradually going to the right forever and ever. So we're going to say that our domain is all real numbers. The range, those are what the y values can be. You can see it's going to be above the x-axis, so y is greater than 0. And if they ask you for the equation of the asymptote, this horizontal line that the graph is getting closer to, this is the line y equals 0. Okay, remember, horizontal lines are y equals lines. Any point on this line, the y-coordinate would be 0. Now let's get into Want to learn Algebra 2? Check out my Learn Algebra 2 video course for sale, where we go through 85 video lessons that take you step by step by step through Algebra 2. We go through the important formulas, concepts, as well as numerous examples to help you master Algebra 2. Click the interactive card or the link in the description below to go over and check out some of the free lessons. Otherwise, let's get back into this current lesson. It would be 0. Now let's get into a little bit more general example. Let's go over here. You can write this formula like this: y equals a times b to the x minus h plus k. What the a does, it's like a vertical stretch or compress. So if a is greater than 1, we call it a stretch. If it's between 0 and 1, we call it a compress. If it's negative, it's going to reflect that graph over the x-axis. It's going to make all the y values the opposite sign. Now the h and the k, the h picks up the graph and it shifts it left and right. So you can think the number grouped with the x shifts it in the x direction, but it has the opposite effect. So if this was x minus 1, it would actually go positive 1 to the right 1. If it was x plus 2, it would actually go left, okay, -2. And then the k is the vertical shift that shifts it up and down. If it's positive, it goes up. If it's negative, it goes down. So just remember, this one has the opposite effect. This one has the same effect. So let's show you a basic example here to start. Y equals 2 times 3 to the x plus 1 minus 3. Now notice this looks a lot like this graph we did here. The only difference is the plus 1 shifts it left 1, and the minus 3 shifts it down 3. So what I'm going to do is I'm going to draw an open circle at -1, -3. I'm going to think of that as our new starting point or our new origin. And you can also draw in your dashed line here, your horizontal asymptote. That's the line the graph's going to get closer to. Once you take that shift into account, you can kind of ignore these values and just focus in on the parent function. Make a table of values, okay, just using that parent function. But instead of plotting from the origin, plot from that shifted origin. Okay, everything shifted to the left 1 and down 3. We're going to pretend like this is our starting point. So from here, I'm going to go -1, 2/3. So left 1 up 2/3, a 0, 2 right there, and a 1, 6. 1, 2, 3, 4, 5, 6, right about there. So you can see the graph's looking something like this. Okay, and notice that your horizontal asymptote here is at y equals -3. The domain is all real numbers. You can see it's going to the left and right forever and ever. But the range is y is greater than -3. See, above this line, y equals -3. So that's the basic idea behind graphing exponential graphs. Remember that variables in the exponent, that's a tip-off that it's going to be an exponential function. Now, let's go ahead and take it one step further. Some applications, we have what we call the exponential growth model or the exponential decay model, and it's an equation that's in this form right here. Y equals a times 1 plus r to the t, or y equals a times 1 minus r to the t. Now the a is like your starting amount. It's like your initial condition. It's like when x is equal to 0, what's that y value? What's that starting amount? But 1 represents 100%, so it represents the original amount. And if you're adding some value, let's say like 0.02, that means that it's going to be 1.02, which means it's greater than 1. And remember when we said when it's greater than 1, it's going to be a growth function. So that's if the rate is greater, if this whole quantity is greater than 1, it's going to be growth. So the rate is the rate of growth or the rate of decay. So if you had like a 5% decay, this would be 1 minus 0.05. If it was a 5% growth, this would be 1 plus 0.05. And then you raise it all to the t power, and the t is the time generally in years. So you have your starting amount, your growth factor or decay factor is this whole quantity. The r is just the growth rate or the decay rate, the percentage converted into a decimal, and then the t is the time in years. So let's look at an example. Say, for example, you had a $20,000 car that was going down by 20% per year, depreciating. And you want to know what the value of the car would be in 5 years. So what you would do is you'd say, well, okay, our starting amount is $20,000, right? But it's going down by 20%, so that's 1 minus 0.20. If it was going up, we do 1 plus 0.20. And we're going to raise this to the 5th power because that's 5 years. Now we can go to the calculator and do this, but I've already done this for us. It's $6,553.60. Okay, perfect. So that's what your car would be worth in 5 years if it keeps going down by 20% each year. Now, one other application that we're also going to practice is the compound interest formula. And compound interest, we've talked about in Algebra 1, simple interest, but here we're talking about compound interest where, you have an amount that you're investing, and then each time period you get some additional interest that you add to the principal. So it's kind of like a snowball. It's like growing, and then you take that larger amount and you add some additional interest, and then calculate the interest on that new even larger amount, and so it snowballs. And what happens is that you get this exponential growth happening because you keep adding that interest to the original principal and calculating the new interest on that larger amount, right? So our basic formula is this one right here you want to memorize. So there's a few formulas in this section to memorize, but you have P, which is your principal. Principal just means your starting amount. 1 represents like 100%, like the original amount, plus the interest rate, R, as a decimal. So you convert that to a decimal. N is the number of times that you compound in a year. So say, for example, it was daily, N would be 365. If it was monthly, N would be 12. If it was weekly, N would be 52, etc. Quarterly, N would be 4. And notice that this N and this N are the same. Okay, so if this was 12, this would be 12. And then T is the number of years. So let's look at an example. So say, for example, you invest $10,000 at 12% compounded monthly. You want to know how much you're going to have after 4 years. So the way we would set this up is we'd say A is just going to be your ending amount. You start off with 10,000, that's your principal, that's P. 1 plus the interest rate, which is 12%, that's 0.12. N is the number of times you're compounding per year. There's 12 months in a year, so that's 12, all raised to the 12 times 4. Now I want to just simplify this a little bit to help you understand why this works. So if you look at the 10,000, right, that's your starting amount. 0.12 is actually, divided by 12 is actually 0.01. And 1 plus 0.01 is 1.01. and 12 times 4 is 48. Now let's think about this for a minute. We said that the interest rate is 12% for the year. But if you're compounding monthly, what that means is that you're getting 1%, see 0.01, 1% per month. And you can see 1.01, see 1 is like 100%, 1.01 is like 101%. So what's happening is, see how this base is greater than 1? It's an exponential growth. It's growing by, a little bit more than 1 each month, right? And so what's happening is you're actually compounding not 4 times, that's 4 years, we're actually compounding 48 times because there's 12 months in a year times 4 years, it's actually compounding 48. It's like pushing that snowball 48 times, right? So again, that's basically why the formula works, but you want to memorize what the different values are and substitute and then just simplify. You can use a calculator for this. We can do that on the calculator. I did this for us already, and it comes out to $16,122.26. Okay, and you want to round. When you're working with money, you always want to round to that hundredths place. That's the pennies. So let me erase the whiteboard. I'm going to have some practice problems you can do on your own to get some experience and practice. And of course, we'll go over those together. Let me do that, and we'll get into those practice problems. Okay, see if you can pause the video and practice these problems, and we'll go over them together. So the first 4 questions are all about graphing. And what you want to do is you want to graph the exponential function, state the domain and range, and then write the equation of the asymptote as well as graph the asymptote on the graph. So let's start with number 1. So y equals 1/2 times 2 to the x power. How would you graph that one? Well, if I was going to do this one, what I would do is I'd just make a table and I'd pick some easy values like -1, 0, 1, and 2, some small numbers. If I put -1 in here, I get 2 to the -1. Remember, the negative takes the reciprocal, so that's going to be 1/2 times 1/2, which is 1/4. If we put 0 in, 2 to the 0 is 1, times 1/2 is 1/2. If we put 1 in, 2 to the first is 2, times 1/2 is 1. If we put 2 in, 2 squared is 4, times 1/2 is 2. Now, if we plot these points, you can see we're going to get left 1 up 1/4, 0 up 1/2, 1, 1, and 2, 2. So what you can see is this graph is growing like that. And you can see it's getting closer and closer to the x-axis. I'm just going to draw that as a dashed line. That's the line y equals 0. And the domain is going to be all real numbers because it's going to the left and the right forever and ever. But the range, the y values, are going to be y is greater than 0, so above the x-axis. Now, just a quick note. Notice the 2 is greater than 1. That means it's exponential growth. The 1/2, because it's less than 1, between 0 and 1, it's compressing the graph. So that's why it's not going up as fast, because the 1/2 is, like squishing it, right, or squeezing it. And it hasn't been shifted, because notice we don't have an h or a k value. So that's the basic graph, you got it. So let's look at number 2, y equals -3 times 1/2 to the x. How would you graph that one? Well, if I was going to do it, same idea, I'm going to make a table. Pick some easy values. -1, 1/2 to the -1, we take the reciprocal, that's going to be 2 times -3 is -6. 1/2 to the 0 is 1 times -3 is -3. 1/2 to the first is 1/2 times -3 is -3/2. And 1/2 squared is 1/4 times -3 is -3/4. Now, if we plot these points from the origin, because it hasn't been shifted, we're going to go left 1, 1, 2, 3, 4, 5, 6. We're going to go 0, -3. We're going to go 1, -1.5, which is right there, and we're going to go 2, -3/4, which is right there. Now, this one, the asymptote is right on the x-axis. That's the line y equals 0, okay? And the graph is looking something like this. Now, you're probably wondering, why does it look like that, right? Well, notice that the a value is negative. See, normally, when you have a graph with a base between 0 and 1, that means it's going to be a decay. It's going to look like this, right? Something like that. And then what we're doing is we're reflecting it over the x-axis. So that's why it has this type of shape. It's still getting closer to the x-axis. The 3 is stretching it. And again, the 1/2 means that it's a decay. It's just that it's been reflected. Okay, so let's go to number 3. So now this one's a little bit more challenging. We've got y equals 4 to the x minus 2 plus 2. Oh, I forgot to do the domain and range on number 2. So the domain is all reals for these exponential functions, but the range is y is less than 0. See, it's below the x-axis, so we're saying the y's are less than or lower than 0. Okay, but for this one, what do you think? Go ahead and pause the video. Y equals 4 to the x minus 2 plus 2. How would you graph it? State the domain and range, etc. If I was going to do this problem, I would notice it's shifting right 2. Remember, this minus 2 has the opposite effect, so it's going to go positive 2, and the k value is positive 2. It's going to go up 2. So that's going to be like our new starting point. That's going to be like our new origin. Okay, and now our parent function is just this y equals 4 to the x power. If we make a table of values, -1, 0, 1, 2, we're just going to use the parent function. 4 to the -1 is 1/4. Remember, the negative exponent doesn't make the number negative. It just says to take the reciprocal. 4 to the 0 is 1. 4 to the first is 4. And 4 to the second is 16. But remember, we're going to plot these points from our shifted origin because everything's picking up and shifting right 2, up 2. So from here, we're going to go left 1, up 1/4, which is right about there. 0, 1, which is right about there. Right 1, up 4, 1, 2, 3, 4, right about there. And 2, 16 is really going off the graph, but you can see that this graph's looking something like that, right? And this asymptote, this dashed line, this imaginary line, is going to be the line y equals 2, okay? You can see how this shifted up 2. And the domain is all real numbers, and then the range is going to be y is greater than 2, but not equal to. So it gets closer to 2, but doesn't touch that asymptote, which is just above. Okay, so great job. So let's look at number 4. This is the last graphing one. Y equals 2 times 1/3 to the x plus 3 minus 1. How would you graph that one? Well, if I was going to do this one, I can see it's shifting left 3 and down 1. So 1, 2, 3, down 1. Remember, the plus 3 actually means it shifts the opposite. So left 3, -3. So our asymptote is going to be right here at y equals -1. And I'm going to focus in on the parent function. This gives us the shape of the graph. The 3 and the -1 are just shifting the graph. And I would just make a, just an easy table here. So let's pick some easy values like -1, 0, 1. Let's see, -1, 1/3 of the -1, that means it's going to be 3 because we're taking the reciprocal, times 2 is 6. 1/3 of the 0 is 1 times 2 is 2. Remember, anything to the 0 power is 1. And notice I'm doing the parentheses exponents and then multiplying. And then this is going to give us 2/3. So from here, left 1, 1, 2, 3, 4, 5, 6, right about there. 0, 2, right about there, and 1, 2/3 right about there. So what's happening is this graph is going down to the right. It's an exponential decay because the base is between 0 and 1. Sometimes people get confused. They see the 2 and they think, oh, this is growth because the 2 is greater than 1. But you're interested in the base, whether it's between 0 and 1 or greater than 1. So definitely a decay. The 2 is stretching it. Okay, and then the 3 and the -1 are shifting it. So the domain is all reals, like all the other ones, but the range, the y values, are going to be greater than -1. See, above this line, y equals -1. Okay, a couple story problems now. Number 5 and number 6. The number of people in a town increases by 2% each year. There are 3 million people currently. How many will there be in 4 years? Okay, so it's increasing by 2% each year. Now remember, we talked about the exponential growth model and the exponential decay model. That's what we're using in this problem. So what do you think? How would you solve this? How many people are there going to be? If I was going to do this, we're starting with 3 million. So let's just call that 3. We'll just write this in terms of millions. It's going up, so we're thinking plus. If it was going down, we'd be subtracting. 2% is 0.02, and we want to know how many there are going to be in 4 years. So we can simplify this a little bit. And if we go to the calculator and simplify, although I did this one earlier for us, it's going to be 3.25, approximately 3.25 million. Okay, so that's it for that one. Now, number 6, it says you deposit $7,000 in an account that pays 4% interest compounded quarterly. That's a key word there. How much will you have in 5 years? So what do you think for this one? Now remember your compound interest formula. And by the way, as you're going through this course, I hope you've been keeping a separate sheet for all these different formulas, just so you can review them, memorize them, and revisit them. But this is the formula we're using here. So what do you think? How much would you have in 5 years? Well, if I was going to do this problem, since we're starting with $7,000, that's our principal, that's P. It's going up by 4%, okay, and that's your interest rate, but it's being compounded quarterly, so that's 4, okay, 4 quarters in a year. Every 3 months is called a quarter, so 3 times 4 is 12 months, that's a year. And then let's see, this end and this end are the same, so that's going to be 4 times 5 years. So there's really compounding 20 times because there's 4 quarters in a year times 5 years, that's 20 times. And this is going to come out to 0.01 plus 1 is 1.01. I'm just simplifying this a little bit down. You don't have to do this. You can put it all in your calculator in one step. And then if we go to the calculator, I calculated this one a little bit earlier, it's coming out to $8,541.33. And remember, you want to round to the pennies. That's the hundredths place, the second digit past the decimal. So great job. Definitely some formulas in here you want to memorize and put on your formula sheet. Otherwise, I'll see you in the next lesson.